Welcome back. In the next series of videos, that will be lesson 6 to lesson 12, we will look at the derivative from first principle of some results. This is purely HL, and so the SL students, you do not need to know this. Also for the HL students, although we are going to find these derivatives from first principle, once you know how to do this, we do not need to all the time calculate derivatives by first principle. So unless you're asked to do this in paper 3 and in some occasions, special cases in paper 2, you do not really need to spend too much time on derivative from first principle. But it's still important for us to know where these derivatives come from the basis of the first principle. So what are we going to do from lesson 6 to 12? We will try to differentiate the following functions. The first one is the radical function. So a and b are generally any real number. N is any integer. Actually, it can also be a rational number. Okay, then we will find the derivative of the exponential function a power x, where a is not 1. We will look at the derivative of log to base a of x, okay, from first principle. And then we will finish with the derivative of arctan x. All right. Now, before we do that, I want us to look at some special mathematical results. The first one that I want to look at is how to show that the limit as x tends to 0 of 1 plus kx, k can be any number really, where k is, this means for all real values of k. All right. E is the natural number. We're going to talk about this shortly. So we want to show that the limit as x tends to 0 of this expression is e to the power of plus or minus k, where plus or minus depends on what we have in here. So if this is plus, then this is going to be e power k. If this is minus, this is going to be e power minus k, which is 1 over e power k. So we want to show that the left-hand side reduces to e power k. All right. Now, e is a natural number, just like pi. 3.14 is a natural number. We say pi is a natural number because it is the ratio of naturally occurring circle, the ratio of the circumference of a circle to the diameter, which remains constant throughout, irrespective of the size of the circle, the radius of the circle, it doesn't matter. The ratio of the circumference to the diameter is always the same, and is 3.14 that. Similarly, the golden ratio, this is called the golden ratio, is also a natural number because it occurs in nature. Flowers usually increase, the petals increase in size outwards in a Fibonacci sequence, that is 1, 1, 2, 3, 5, and so on. So if we find the limit of the ratio of Fibonacci numbers as the numbers tend to infinity, we get the golden ratio. Okay, so similarly, E, which is what we are talking about here, is a natural number. How do we normally find E? If you've gone through financial mathematics, you've probably shown that when we look at compound interest, we know that future value is given by present value, sometimes called the principal, into 1 plus r over 100n, where n is the number of times we compound per year, and then this is power n times t. Okay, so for example, if we are compounding once every year, then n is 1. If we are compounding twice every year, then n is 2. If we are compounding every month, then n is 12, and so on. T refers to the number of years for which we are going to calculate the interest, all right? So if we let the present value be a unit value, so 1, and we let the rate be 100%, then now we have 1 plus r as 100%, so divide by that, we end up with 1 over n. Okay, if we let the time be 1 year, then this just becomes power n. And in financial maths, hopefully you were able to show that this reduces to e, but if you didn't, that's what I want us to show now, okay? All right, this is in fact similar to that. If we let n be represented by 1 over x, then now this is the same as this becomes 1 over x, and this becomes 1 divided by 1 over x, which is just x. So this will reduce to 1 plus x power 1 over x, which is the same as what we have here, which is similar to what we have there. Of course, we can introduce a constant there, k. All right, but generally this is what we have. So what we are trying to say is that this expression here, this is the same as that expression, but this expression occurs, this is the limit as n tends to infinity. All right, but if n is 1 over x, then this has to be the limit as x tends to 0, because x has to tend to 0 here in order for n to tend to infinity. All right, so in this case, if the expression looks like this, then we must say n is tending to infinity. So we are going to compound infinite number of times in a given year. So here we have to say then that x is tending to 0. All right, so now let's evaluate this, hoping you've understood. Okay, so let's then move on. The first thing we're going to do is we're going to let this expression on the left hand side, we will represent it with the letter L to represent limit. So if we represent it with the letter L, then L equals that. All right, then we take the natural log of both sides. Natural log means log to base e, natural log. So the L here implies logarithm and n implies natural. So this is actually expressed in French, where they start with the logarithm and then natural, like that. So that implies natural log, which is also to say log to base of this number that we looked at earlier. And so if we take the natural log of both sides, then we write ln of L, that means log to base e of L must be equal to the natural log of this. We can of course push the ln inside, doesn't have to be out there. It is not affected by the limit. Okay, so if we do that, then we end up with this, but we can use the laws of logarithms, which moves the 1 over x to the other side. That is law number 3 of logarithm. It's called the power rule. So log to any base of x can be expressed as n. So this n here can move to the side and we express it like that. So because of that, we can move the power 1 over x to go to the side of ln there in the same way. And we get that ln of L is now equal to the 1 over x has gone to the side like that. Okay, and now what we do, your HL students, so the next thing we do is we need to find the polynomial approximation of ln of 1 plus kx. So the polynomial approximation is determined using what we call Maclaurin series approximation. So we can generate the series approximation for the log to base e of 1 plus x, for example. So if we do that, the result is up here. If you haven't done that, don't worry. But because we are interested in determining the derivative from first principle, it is not important that we remember this or that we memorize this, okay? Normally it will appear in the formula booklet for mathematics, so you don't need to really memorize that. So if we express ln of 1 plus x like that, this is a polynomial approximation, then the same thing can be done with this expression here, and let's see what we get. So if we write this, ln of L equals log is the limit as x tends to 0 of 1 over x, and now we're going to expand that, compare what we are doing this here with this. Now this is the expansion for this. So the first term there is going to be x. All right. So if we relate with what we have here, then our first term there has to be plus or minus kx. All right. So we will put plus or minus kx. Then there is a minus, and the next term is this x squared divided by 2. So we are going to write our x, what represents x here is plus minus kx. So we will have plus minus kx squared divided by 2. So if I write that down here, so plus minus kx squared divided by 2, then it is plus, well, this is minus because of that minus, and here we are going to have x cubed over 3 because x cubed over 3. So in our case we will have kx cubed divided by 3, like that. All right, and it continues on like that. The next will be power 4 and so on. Okay, so this is the series expansion of this. We don't need all the terms. This continues to infinity, so we just need to write down a few first terms. All right, now the next thing to do is to simplify by opening the bracket. 1 over x goes in there. If 1 over x goes in, it will cancel. So if we multiply in here, it's going to cancel the x and x will cancel, and we are left with plus minus k, like that. Okay, so the first one is plus minus k. Notice 1 over x has now disappeared, so it multiplies there. We are left with plus minus k. If it multiplies in here, this value, this is, so 2 plus minus x squared. Positive squared is just positive, negative squared is also positive, so this term here is going to be positive k squared. So I can write k squared there and x squared, because the square there goes in and is distributed to the k and to the x, and then that is divided by 2. All right, so what we are left with, let me write it nicely. So we are saying that here we will have k squared, right, and x squared there, and positive cubed is positive, but negative cubed is negative, although this does not matter. So at the top here we're going to have k cubed x cubed plus or minus. Okay, it doesn't really matter because this two terms are going to disappear anyway. So if we open that bracket for this one, we end up with, if we open up this bracket for this, the x is going to cancel one of the x there, and we'll have k squared x, right? So the next term is going to be minus k squared x over 2, and the next term is going to be plus, actually it's plus or minus kx cubed, or k cubed x squared over 3, and so on. Okay, so let's move to the next page and write that again properly. I will remove this. Okay, so that's this is the expression we came up with on the previously. So the next thing is now to bring in the limit. So the limit as x tends to 0 of this expression means that this term is now x is becoming 0, so this term can disappear, and x is also becoming 0 here. So any term that will contain x, which is everything from here onwards, they are all going to disappear, and we are left with plus or minus k. So ln of L is going to be plus minus k, because we've now gotten rid of that limit, and so we can write that ln of L is plus minus k. Hoping you understood this. It's not very difficult. Now the next thing, of course, we want our L back, because we had let our expression be L earlier. So we want our L back. To do that, we change this to the index notation. Log to base e of L is plus or minus k, and that means that L is going to be e power plus or minus k. Okay, now what does this really mean? Remember, L was given by these expressions here. So we are saying this expression can be written as that, which is also to say that the limit, so if we just take the positive side, the limit of 1 plus kx power 1 over x is e power k, and the limit of 1 minus k power kx power 1 over x is e power negative k, which is 1 over e power k. Here is a small mistake I made. omission rather than a mistake. So that is e power k, like that. So usually we will have k equal to 1, but in case k is anything else, like k could be any other number, if that's the case, then this is how it is distributed in the final result. Okay, and this is how we have proved that the limit as x tends to 0 of 1 plus minus k x power 1 over x equals to e power 1 e power k, positive or negative. All right, a typical exam question that one would want to ask us on this area is this. So for 6 marks, let L be given by the limit as x tends to infinity. So notice this is x tending to infinity, and this is a over x rather than ax or kx, okay? It doesn't really matter. We discussed this already. So where a is any real number, by considering log of L, so taking the log, natural log of both sides, find the value of L in terms of a. So of course the way to do this is, I think what I'm going to do is to let you try this out yourself, and then we will look at the solution after that, okay? So I will put up a solution at the end of this video. Please try it out first and then check what we come up with for the answer. All right? And so for 6 marks, here's the question. So for 6 marks, we want to determine the value of L in terms of A. To do that, the first thing we have to say is we will let x be represented by 1 over, let's say, a different number, t, where t is a variable just like x. If we do that, then I can now write, so if x is tending to infinity, for x to tend to infinity, if x is to tend to infinity, t has to tend to 0. All right, so for x to tend to infinity, t has to tend to 0. That is also to say that I could express this as t is 1 over x. So where there is 1 over x, here is 1 over x here, I'll put t, and where there is x, I'll put 1 over t. So therefore, my L can now be expressed as limit as t tends to 0 of 1 plus at, 1 plus at, 1 plus at, everything power 1 over t. Okay, so that's what I need to do. The next thing I do is to take ln of both sides. So if I take ln of both sides, I have ln of L must be equal to the limit as t tends to 0 of ln of 1 plus at, everything power 1 over t. Because this is ln, I can use law number 3 of ln and move this 1 over t to the side there, and I have limit as t tends to 0 of 1 over t, 1 plus at power 1 over t. Okay, I can now open this bracket here. So we can open this bracket right here using Taylor-Maclaurin approximation, and this becomes ln limit as t tends to 0, 1 over t, and then I will have, like we said earlier, this is going to be at minus a t squared, so a squared t squared over 2 plus a cubed t cubed power 3 plus and so on. Okay, we can open that bracket like that, and now if I open the bracket with this t multiplies that out, and I have my ln of L. This is still visible. Ln of L is the limit as t tends to 0 of, this opens that bracket, and I have just a plus this, open that bracket, and I have, it's actually minus, not plus there, because of this minus here. So minus a squared t over 2 plus a cubed t squared over 3. And the limit as t tends to 0 means that this term disappears. This term here is going to disappear because t is 0, so this disappears and that disappears, and we have ln of L equals A. So I can now write that ln of L is just A. And that means, if I change this to index notation, L equals e to the power of A, like that. Okay, so this is the sort of question you might get from an examination body like the IB to show your mastery of this processing. Okay, thank you very much. We'll go to the next stage. The reason why we did this first is because we will need it in some of the proof or differentiation from first principle when we do logarithms, log to base a of x, and when we differentiate a power x, we need to be able to do this sort of thing. So that's why I started with this first. Okay, we can now go in and start looking at the derivatives of the various functions we listed using the first principle.